Immunology Insights, Basics and Beyond, Chapter 39, Tolerance Mechanisms in Transplantation. Marcello here. Welcome back to Immunology Insights, Basics and Beyond. In our last chapter, we reviewed the powerful and necessary immunosuppressive drugs that have revolutionized transplant medicine. These medications protect transplanted organs by suppressing the immune response, but they come at a cost. Long-term side effects, increased infection risk, and reduced quality of life. So, what if we could achieve the same graft protection without the need for lifelong immunosuppression? That's the bold and fascinating promise of tolerance induction. Today, we will explore what tolerance actually means, how it arises naturally or can be induced experimentally, and how far we have come in making it a clinical reality. This topic bridges basic immunology and cutting-edge clinical trials. So let's talk science. What is transplant tolerance? Well, transplant tolerance refers to a state in which the recipient's immune system specifically accepts the donor's graft as self, while still maintaining the ability to fight off infections and malignancies. Unlike immunosuppression, which broadly dampens the immune response, tolerance is selective and self-sustaining. In some rare cases, patients achieve what's called operational tolerance, a clinical condition where the graft continues to function stably even after immunosuppressive drugs are discontinued. These individuals provide crucial insight into how tolerance might be induced more broadly and predictably. Let's look at some natural examples of tolerance. There are powerful natural precedents for immune tolerance, reminding us that selective immune acceptance is not just a theoretical idea, but it's biologically possible. First, in pregnancy. One of the best known examples of natural tolerance. The maternal immune system must tolerate the semi-allogeneic fetus, which expresses paternal HLA antigens that are foreign to the mother. This tolerance is maintained by placental immune regulation, local suppression of T cell activity, and an expanded population of regulatory T cells, or Tregs. Second, in liver transplants. The liver has a unique immunological profile. It is more tolerogenic than other solid organs. Especially in children, some liver transplant recipients can eventually be weaned off immunosuppression without losing graft function. The exact reasons are still being explored, but may include the liver's high content of immune regulatory cells, low expression of co-stimulatory molecules, and the ability to regenerate. Now, let's also look at the mechanisms of induced tolerance. Scientific strategies to induce tolerance mimic or enhance natural processes that train the immune system to ignore the draft. These mechanisms target different levels of immune control. First, central deletion, or mixed chimerism. This approach involves infusing donor-derived hematopoietic stem cells into the recipients, often alongside an organ like a kidney. The goal is to create a state of mixed chimerism, where both donor and recipient immune cells coexist in the bone marrow. During thymic selection, T cells that recognize donor antigens as foreign are deleted, establishing central tolerance. However, achieving this often requires myeloablative conditioning, which can be toxic. Second, peripheral regulation, for example via Tregs. Even if donor-reactive T cells escape central deletion, the immune system can still be regulated in the periphery. Expansion of regulatory T cells, or Tregs, helps suppress immune responses against the graft through the production of anti-inflammatory cytokines like interleukin-10 or IL-10 and transforming growth factor beta or TGF-beta. These cells act as local peacekeepers, preventing destructive responses without impairing global immunity. Third, energy and exhaustion. Blocking co-stimulatory signals required for full T cell activation, such as the CD28 to CD80-86 interaction, can lead to energy, where T cells become functionally unresponsive. Similarly, Activation of PD-1 and other exhaustion pathways can render T cells ineffective at attacking the graft. Therapies that intentionally promote these states aim to reduce graft-directed immunity without blanket suppression. Now let's look at clinical trials and the respective progress. Several pioneering trials have shown that tolerance is achievable, though not yet routine. First, at the Massachusetts General Hospital in Boston. In a landmark protocol, kidney transplant recipients were given a combination of bone marrow and kidney from the same donor, following conditioning therapy. Some patients have remained off immunosuppressants for over 10 years without evidence of rejection, thanks to stable mixed chimerism and immune adaptation. Second, the HESTIA trial for lung transplants. Investigators infused autologous Tregs, so regulatory T cells derived from the recipients, shortly after lung transplantation. Results showed a reduction in early rejection episodes, suggesting that boosting Tregs at the right moment may tip the immune balance toward tolerance. Third, biomarker studies. Research into immune biomarkers is helping to identify tolerant patients. High expression of molecules like FOXP3, which is a Treg marker, CTLA4 and IL-10 in peripheral blood or graft tissue may predict or reflect a tolerant state, though standardization is still lacking. Of course, there are also challenges and caution is to be applied. Despite the promise, tolerance induction faces serious hurdles. First, toxic conditioning. Most tolerance protocols involve chemotherapy or radiation to allow donor stem cells to engraft. These regimens are not without risks, including infection, cytopenias, and organ damage. Second, graft versus host disease, or a GVHD. When donor immune cells attack the recipient, as in bone marrow transplantation, GVHD can occur. Balancing mixed chimerism without triggering GVHD remains a delicate task. By the way, here's a quick immunology note. This is the opposite to the before discussed host versus graft reaction, where the recipient's immune system attacks the transplant. In graft versus host disease, it's the donor's immune cells, especially the T cells, that attack the recipient's tissues. Both can be devastating if not controlled, and today's topic directly relates to minimizing these risks. Third, risk of premature withdrawal. Stopping immunosuppression too early, even in seemingly stable patients, can lead to sudden and irreversible rejection. More reliable biomarkers and monitoring tools are needed before tolerance protocols can be applied widely. So, what are future directions? Researchers are exploring novel technologies to induce tolerance without the toxicity of current approaches. First, for example, CRISPR gene editing. Engineered hematopoietic cells may one day establish chimerism without triggering GVHD by removing or modifying key immune genes. A second example are nanoparticles. Tiny particles loaded with donor peptides and immunomodulatory agents are being designed to deliver targeted immune training directly to lymphoid organs like the spleen or the lymph nodes, potentially inducing tolerance in a localized and non-toxic way. These technology examples are still experimental, but represent a significant leap towards safer and more scalable tolerance induction. To conclude, transplant tolerance is one of the most ambitious goals in modern immunology, a future where patients can receive life-saving organs without needing daily drugs to suppress their immune systems. If achieved, it would eliminate many of the complications that come with immunosuppressive therapy and improve both graft longevity and patient quality of life. Although we're not yet there, clinical trials and emerging therapies offer real hope. By better understanding and harnessing the immune system's natural ability to tolerate, we move closer to making the vision a reality. In our next chapter, we will look at graft engineering and stem cell enrichment. cellular level strategies that can support tolerance and improve transplant outcomes from the inside out. Before closing, I have a small request. If you enjoyed my content and want to hear more, like and subscribe. It's a small step for you, but it helps me a lot. So, see you next time and thank you for listening.